Welcome back. In the previous week, we looked at a technique of counting called the principle of inclusion and exclusion. We saw several applications of this method. Now, we want to look at the same technique, maybe with a slightly different viewpoint. And the idea is to generalize this even further. So, before going further, let us look at what is called inversion formula. So, what is an inversion formula? So, suppose you are given a function g that is expressed in terms of, let's say, some other function f. Now, an inversion formula is a formula that computes the function f in terms of g. So, you are given a formula g in terms of f. Now, you want to find out what is f in terms of g. So, this is an inversion formula. Right? So, let us look at a very basic example to begin with. Suppose you look at, let's say, g of x is equal to summation I is equal to 1 to n f of I. So, this is given to you. For every natural number n, you have this defined. Okay? So, g is defined for every natural number n, and it is summation I is equal to 1 to n f of I, where f is some function. Now, the question is that can you recover f given g, right? If you know g, can you recover f? So, this is something you must be pretty convinced that you can find it very easily. To think about it for a minute, you can see that we can write f in terms of g as follows. So, f of 1 is g of 1, of course. From this summation, it is very clear. Then f of n can be written as g of n minus g of n minus 1. Okay? This is also something that you can verify immediately from the previous definition of g in terms of f. So, but this is slightly more than that. You can, if you remember your calculus, you can see that this is a discrete analog of the fundamental theorem of calculus. Right? That is what we say in calculus also. The fundamental theorem of calculus expresses the one function in terms of the difference of the other at the endpoint. Right? So, one can try to prove, in fact, the non-discrete version also using this kind of an approach, but it takes a little bit of work, but it's possible, I believe. Now, an example, one more example, let us look at. Suppose S is a set of properties that elements of some given set, let's say A, may or may not possess. Okay? So you have a set, a big set A of sets, several sets maybe, right? Or some other elements, whatever. But now you collect some properties that some of the elements of this set might have or might not have. So you take all these properties and say that, okay, these elements have this property, these elements have this property, these elements have this property and that property, like whatever. So you have this collection of properties that each element may or may not have. Then suppose some function f counts. So suppose you are given a subset of S, let's say T, then f of t counts the number of elements in A that has exactly the properties that is described in T. Right? So the properties, T is a subset of S, so T describes certain properties. Now f of t counts those elements that has exactly these properties and nothing else. So the other properties this does not have, right? Only these properties it have, precisely these properties. So whatever that number is, that is counted by f. Now, so yeah, so when I say exactly counting exactly, I mean is that they fail to have properties in S minus t, because S is the set of all properties that we are considering, and ft counts only those precisely in t. Now g of t, let us say, counts the number of elements in A that has at least all the properties in T, right? So G basically counts those properties where, take those elements. So you take all those elements where these elements have all the properties in T, that is given, but it can have other properties. We don't care about that, but it should have all the properties in T. So now one can immediately see that G of T can be expressed in terms of f very easily, right? So you take, all supersets of T, right, and then say that sum over all this f, and that will give you G, right? Because f of x counts all those, so for the set x, all those having precisely the properties x, and now G of T is basically now summation over all x, which is a superset of T, f of x, which means that it will have all the properties, all the elements having properties in T and more. Right? So that is what G of T is. So G of T can be expressed as summation f of x, where x is containing T. Now, what the principle of inclusion-exclusion says is that you can find the inverse. That is, you can express f in terms of G also. Right? So if you recall the principle of inclusion-exclusion, what the way we used it, and think about exactly what we were doing, that we were expressing expressing, so we wanted to find some the number of elements having precisely some property, and then we said that okay, we count those which has at least these many properties, and then we use that to get a formula for the properties that is precisely in this given set, right? So if you are not convinced, go back and think about it, look at some example and see whether it is precisely the same thing. Okay. So what principle of inclusion exclusion states is the following, that f of t is equal to summation over all x containing t minus 1 raised to cardinality of x minus t g of x. Now we did not state it precisely in this form, but you can see some similarity, and if you work out the details, you can verify that this indeed expresses the principle of inclusion and exclusion. Okay, so we will come back to it again, but for the time being, I want you to go through this this version or this point of view, and then see whether it matches with this, this expression matches with the way we have defined the principle of inclusion and exclusion. So think about this, and also think about this way of thinking, that as two functions f and g instead of the way we presented earlier. Okay. So and what we are doing is actually a kind of inversion. Okay. So once you think about it, it will be very clear. Then now I want to look at this also in a different viewpoint. So the classical way, or not classical, not just the classical, the standard way or the more popular way of introducing principle of inclusion and exclusion is by looking at the small examples, like you have 2 sets or 3 sets. Then you take to count, what you are doing is that, okay, you count the union. You take the union, and then you subtract the intersection of pairs, and then you again go back and then add the things that we have subtracted too many times, right? So this way, and then try to generalize that into a formula, right? This is what we did, and when we try to prove this from the basics, and of course it is the way probably the technique evolved also. But then this technique, once you see it in terms of as an inversion, you see something more to it, and then you can realize that it's actually a very minor theorem from linear algebra. So inclusion-exclusion principle is just a small theorem in linear algebra, and it became so important because of its wide variety of applications, wide applicability, right? And so let us see how this is a theorem in linear algebra. So, so here is the theorem. Let S be an n element set, and V be a vector space of dimension 2 raised to n of functions that go from, or that maps the elements of the power set of S, right, which is if S has n elements, then power set of S has 2 raised to n elements to R. Basically, it's a real valued vector space over the power set. Now, look at a linear transformation phi that maps V to V the following way, that phi of f of t, right? So f is already a function. Now phi of f of t is summation over all x containing t f of x. Okay. So this is the way the linear transformation works for any given t subset of s, right? So given a t subset of s, f of t, so because the domain of f is the subsets of s, so therefore t subset of s means that the function is defined for that, and therefore this is a well-defined linear transformation. Now, if you define the linear transformation this way, the theorem states that its inverse exists, phi inverse, and the inverse can be given by the following. Okay, so phi inverse of f of t again is equal to summation over all x containing t minus 1 raised to modulus of x minus t f of x, where t is any subset of x. For every subset of s, you have this. So again, complete description of phi inverse. So this theorem is precisely what the inclusion-exclusion principle is saying. If you just compare it with the previous statement, you can see immediately why this is the same statement. And let's prove this. So the proof is by assuming that, okay, if there is an inverse, they said that this is the inverse. So let us take this as some function. Let's say psi maps from V to V is psi of f of t is equal to summation x containing t minus 1 raised to mod x minus t f of x. So this is the definition of psi. Now we show that psi is the inverse of phi by multiplying them together and seeing that it returns identity, right? So let us say that what is phi psi of f of t. Okay. So phi psi of f of t is by the definition summation x containing t minus 1 raised to mod x minus t phi f of x. Now phi f of x is summation z containing x f of z So therefore, you get this double summation. Now, so you take this and then you realize that, okay, so x is containing t and z is containing x. So therefore, I can write as summation over all z containing t. And summation z containing x containing t minus 1 raised to mod x minus t. Now this part is independent of the choice of the z, so therefore I can compute it. And what is that? For computing that, I put m is equal to modulus of z minus t, or cardinality of z minus t, which is required to write it as in the counting in a different way. So let us look at what is the the internal bracket here sums to. Okay. So that sums to summation z containing x containing t minus 1 raised to mod x minus t. So look at the x in terms of like so x can vary from but t to z, right? So when x is equal to t, you will get 0, and when x is equal to z, we will get m, right? So now we count according to the cardinality of the set that we are considering. So now we can say that this is equal to, or cardinality of x minus t. Then we can say that the summation I is equal to 0 to m. M choose I because precisely M choose I ways to select an I element set in this case, and minus 1 raised to I. And this is equal to, what is this? By using binomial theorem, one can see that this will be precisely 1 when m is equal to 0 only, and every other cases it is going to be 0. Okay, so when m is equal to 0, this will be the summation will be 1, and when m is different from 0, the summation will be 0, because this is basically 1 minus 1 whole raised to m. So therefore, we get this as the Kronecker delta 0m. Now, so the internal part is Kronecker delta 0m. So now look at what happens here, right? So when is this precisely non-zero, that is when m is equal to 0, right? So when m is equal to 0, this is non-zero. So therefore, the only term that survives is m is equal to 0. So what is m is equal to 0? That is z is equal to t. So therefore, in the summation, the only term that remains is or survives is f of t, and everything else disappears. And in that case, the summation here is precisely 1. So therefore, we get f of t. So on the right hand side. So therefore, phi psi f of t is equal to f of t, which means that phi psi is the identity, or psi is the inverse of phi. So that proves the theorem, right? So it's a very simple proof, and this is a result from linear algebra, and you see that this statement is precisely our statement of the principle of inclusion and exclusion, right? So you can express f in terms of g. So given given a function g, which is in terms of the in terms of the function f, which counts exactly the properties in subsets, then you can express f in terms of g also.